Okay, grade 11 chemistry. This is our second video. This is going to be all about periodic trends in the periodic table. But first we're going to do a little bit of review. So first a brief review of Lewis structures. Then we'll talk about the basic trends in the periodic table. Why is the table periodic? We'll talk about electrical force, a little bit of physics. I have a little demo involving a balloon. And something called effective nuclear charge, which is going to help us explain the trends that we're going to see afterwards. The three trends that the curriculum is interested in is ionization energy, electronegativity, and atomic size. We're going to do these two together because they're very related, and then atomic size is somewhat related but a little bit different, so we'll have it on its own. Yeah, so let's just jump into it. We'll have our brief review of Lewis structures first. So going over to the PowerPoint here. A quick review. We want to draw the Lewis structure of sodium and the Lewis structure for chlorine. And I'm going to jump over to the whiteboard. And we want the Lewis structure of sodium and the Lewis structure of chlorine. So sodium is sodium, and chlorine is chlorine. Like that. We have our periodic table here. Right, when we look at the table, sodium is here in the third row, in the first column. And kind of the shortcut is every time you start a new column, you're starting a new electron shell. So if it's in the first column, it's the first shell. So it's the one electron in that shell. So there's the sodium Lewis structure. Chlorine, on the other hand, is all the way over here, right? It's 7. 1, 2, 3, 4, 5, 6, 7. So it's got 7 valence electrons. Or you can just use the shortcut that this is group 17, and everything in group 17 we say has 7 valence electrons because the transition metals we skip over them. So chlorine, right? 7, and to put 7 on it, you have to spread them out because electrons repel each other, but they pair up after they've spread out around. So looks something like that. That's an appropriate Lewis diagram for chlorine. What I'm going to do also here, because it'll help us explain it'll help us explain the trends later, is I'm going to draw the Bohr diagram of sodium and of chlorine. So I'm going to draw the Bohr diagram of sodium. When we look at sodium, right, it's number 11 with a mass of 23. Number 11 with a mass of 23. So that means 11 is the number of protons, because that's what gives it its mass. The mass, that's what gives it its properties. 11 protons is always sodium, no matter how many neutrons are there. A mass of 23 means that there are 12 neutrons in the core. Being in the third row means that there are 3 electron shells. So we're going to draw our 3 electron shells. 1, 2, 3. First shell has 2 electrons. Second shell has a full 8 electrons. The third shell has just that 1 electron. I'll put it up here. We'll put it there. Okay, chlorine's going to look similar. It's got 3 shells because it's also in the third row. And now it's got 7 valence. So it's going to look a lot similar. So let's draw that here. Chlorine is number 17 on the table. Number 17. So 17 protons. It has an atomic mass of 35.5. We're going to round it down to 35. We'll talk about isotopes later, but yeah, 17 protons and 35. So 35 minus 17 is 18. 18 neutrons. It's also got 3 shells because it's in the third row. 1, 2, 3. And the same arrangement, right? 2, 8, 8. the same thing as we see up here, the same kind of structure. So we're going to use that later to explain a little bit about its about the trends, about the size. Notice that I drew chlorine a little bit smaller than I drew sodium. That was on purpose. Chlorine is actually smaller than sodium as an atom. So that's a quick review of Lewis structures. Reminder that the valence shell is the only shell involved in chemical reactions. That's why Lewis structures are so useful, because they're quick to draw and they're more predictive. So that's the end of that. We're going to move on to our learning goal, which is basic trends, just the start of trends in the periodic table. So I'm going to pause and fix that up. Okay, so we're talking about basic trends in the periodic table. I'll move this over here. Basic trends in the periodic table. These were obviously done by experiment. Lots of people combining elements with each other, see what the ratios were. This is all after Dalton and the law of definite proportions. It's obviously a table, but why is this periodic? What's periodic about this table? Right? What's periodic about this table? Well, periodic is something that repeats over a certain period of time. Right? That's where period comes from. Period is the amount of time for the repeat, or the amount of anything for the repeat. In this case, what people saw when they were looking at the table is they noticed certain patterns, right? So valences is one that we've already seen. And we've already seen this thing where all of these ones in group 1 have a valence of 1, and group 2 have a valence of 2, group 3 have a valence of 3, 4 has that valence of 4, 5, 6, that kind of thing. This is where the transition metals come from too, right? That middle section, the transition metals, the valence trend seems to skip from here to here, and so they put this in its own block. So that's a trend we've already seen, and it repeats every time we come back to, lithium, and then repeats at sodium, repeats at potassium, and so you can build up a table from there. The big guy for periodic trends was Dmitry Mendeleev, who was a German-Russian scientist. He was the first guy to make a table that really fit the trends nicely. And there's this quote from him that I love, because the table came to him kind of in a dream. Right? I saw in a dream a table where all elements fell into place as required. Awakening, I immediately wrote it down on a piece of paper. Only in one place did a correction later seem necessary. So this concept of 8 groups. All right, he's got group 1, 2, 3, 4, 5, 6, 7, 8. The group of these 8 groups, and the rows. It's a little bit weirder compared to our current table, but that's but that was the first one that actually had trends in it, of a repeating series of trends. Why are the trends important? Well, it helps us predict properties of elements. So knowing these trends, studying how it changes as the amount of protons and neutrons and electrons changes, you could maybe make predictions on what kind of elements we can see, or predictions of elements that you might want to try as a substitution for something. So, for example, Mendeleev actually predicted the existence of several elements. You see these dashes in his table. These dashes are elements that he said should exist, but haven't been discovered yet. The most famous one is this one here with the 72. He called it eka-silicon because silicon is here. So eka-silicon means like next silicon, and he said, well, silicon's 28, and tin here is 118, so it should be somewhere between those two. It should be like tin. It should make an oxide of RO2 because it's in group 4. Oxygen wants 2 bonds, and so this thing would have 4. That's where the 4 comes from, right? We talked about bonding a little bit. So yeah, here's his predictions, right? He predicted mass of 72, dioxide, so O2, which it does, and various other things. He predicted its boiling point, its density, predicted, he got close. And this was why Mendeleev was celebrated. He was able to actually, give them ideas of what to look for. And he's like, hey, if you find something that has these properties, it's probably a new element, and you get to name it and stuff. So that became known as germanium. Yeah. So it's kind of cool that he was able to make a prediction all the way back in 1870. Yeah. Interestingly, because Mendeleev was Russian-German, Russians still use this kind of organization for their tables sometimes. I'm going to find a picture of that and I'll put it up. Just give me a sec to pause. Yeah, here you go. Here's a modern table from a Russian news site, and you can actually see that they've organized it a lot like Mendeleev's table. Like, here's Mendeleev's table. There's Mendeleev's original table. And if we go back to that Russian website, they actually, they have a lot of the new elements, but they can organize them like that as well. A little bit different from the table that we typically see. Now, of course, the Russians also use this table as well, just with Russian names for the elements. But it's neat that there are different organizations that can be done with the periodic trends. So they have a lot more rows and a lot less columns, a lot fewer columns. Yeah. All right. Back to this. So yeah, that's predictions and basic trends. Here's a common trend to observe. It's the reactivity of alkali metals. If I click this, right, there's this classic video from Brainiac.
Whether you've left school or you're still at school.
Now this is actually an entertainment video. This Brainiac video. So that's actually wrong. What I will do is I'll link this one, the accurate version, down below. And you can watch that trend. But essentially, the further down the alkali metals you go, so lithium, sodium, potassium, lithium, sodium, potassium, rubidium, cesium, and francium, the further down you go, the more violent their reaction gets with water. It's pretty interesting. So I'll link some real experiments for that, demos with that down below. They also get softer. Lithium is relatively hard. Sodium can be easily cut with like a spoon. Potassium also, even softer, can be cut with a spoon. And then rubidium and cesium are actually practically liquid at room temperature. I think cesium has a melting point of like 25 degrees Celsius or something. It's very, very, very close to being a liquid at room temperature, but it isn't, because the standard state is like at 20 degrees Celsius or something like that. Yeah, so that's the reactivity of alkali metals, a very classic trend. And we'll explain why. We'll explain why they get more reactive as they go down. So this is where we start the next section, which is an overview of electrical force concepts and effective nuclear charge. So I'm going to pause and fix that up, and we'll start things off with a demo. So that'll be cool. Okay, so we're talking about the electric force, and the first thing I want to do is a little demo about the electric force. And what I want to show you is the things that affect the strength of an electrical attraction between two objects. So I'm going to take away the learning goals, and what we're focusing on here is the electrical attraction between two objects. So I've got my balloon, right? I've got my balloon. What I'm going to do is rub it on my hair, classic. If I just rub it, a little bit, I get a little bit of attraction to my hair, right? You see it's attracted to my hair a little bit there. There's just 2 rubs. This is because now there's electrons on the balloon and less electrons on my hair, so there's been a transfer. So now the balloon is negatively charged, my hair is positively charged. Right. What happens if I rub it more, right, and kind of get it all over? What do you think will happen? You'll notice that it's only in one place. It's kind of fun. Depending on where I turn the balloon. If I rub it more electrons will transfer. So that's the first thing is, as the amount of charge increases, obviously the electrical attraction will increase. So if I really do really get in there, right, now it's able to pull up a lot more of my hair. And, you know, from a further distance and stuff too. So that's the first thing, right? The first thing is more charge means more force. And as you might imagine, twice the charge means twice the force because there's twice as many charged particles. So it's a linear increase with the amount of particles. So we'll talk about that in terms of atoms in a second, right? So that's, yeah, very, very strong though. Right. Now the second thing though is the relationship with distance. And if you see up here, right, the electric force drops off very quickly with distance. Here it's, you know, that far away from my hair. If I go higher up, very quickly it stops affecting my hair, right? And this force is not linear, right? It's not like it's half here, because if I bring it twice as close, it's more than twice as attractive, right? It's not linear. What it actually is quadratic. When I'm twice as far away, it's 4 times less force. When I'm 3 times further away, it's actually 9 times less force. So very quickly, I just lose all of that attraction to my hair. But if I bring it in close, right, there's my hair trying to reach up to the balloon again. Maybe a more interesting version of this, and maybe more relevant to our chemistry thing that we're doing now, is if I put it on my hand like this, right? I put it on my hand, and I bring my other hand up here. It is being pulled towards the Earth by gravity, but I can overcome that attraction by bringing my hand close, right? And up it goes. You saw it float up to my hand. So when I get close enough, I can actually override one attraction, which is the attraction of it with the planet. I'll bring it down so that you can actually see the attraction better. See, it comes up from a certain distance. I'm not doing anything special there. It just matches up to my palm. And I can, you know, it's kind of magic. So with more charge, I could probably do this from further away, right? Which is great. But if I even get a little bit further away, it drops off incredibly quickly with distance. Then the strength of the gravity overrides the attraction. And so, yeah, you can do stupid stuff like stick it to the side of your face and maybe it'll stay there. Let's see. Oh no, it likes my body more than my face. Anyway, that's electrical force. Electrical force goes up with the amount of charged particles, goes down greatly with distance, with the square of the distance. So, question is, what does that mean for atoms? What does that mean for chemicals? Well, let's jump over to the document camera where we have our sodium and our chlorine, and we want to talk about something called effective nuclear charge. Effective nuclear charge. I'm going to write that down. I realize it's in the bottom corner here, but effective nuclear charge, right? Effective nuclear charge. Now, break it down. Effective meaning, how strong. Nuclear meaning the nucleus, and charge meaning charge. So what we're going to do here is we're going to modify this nucleus, and I don't really care about the number of protons and the number of neutrons. I care about its charge. So, in terms of charge, sodium has 11 protons. So that charge is just 11. 11 positives in the center. And chlorine has 17 protons. So its effective nuclear charge is 17. Or its nuclear charge is 17. But that's just part of it, right? That's just the nuclear charge. That's just the nuclear charge. How does the effective piece come into it? Effective nuclear charge. So for the nuclear charge to be effective, it has to pull on all of the electrons at once. And the thing to kind of realize is it's not like the charge is divided between each electron. It's like, you know, the gravity of our planet, of Earth, is not like it's not like that force is divided between each person. Everyone just feels an attraction to the center, and everyone feels, you know, the same one. It's not like if we add more stuff, there's less attraction for everybody. It's the same attraction for every electron. If you add another electron, it's not like the rest of them feel less attraction, is kind of what I'm trying to get at. So they all feel attraction to the nucleus, and the outside ones are going to feel less. Why do they feel less? Well, because it drops off very quickly with distance. And in terms of effective charge, what we need to think about is which of these electrons, outside electrons specifically, right? There's this guy. Well, let's try to grab a different color here. There's this guy, right? That electron. And then there's these electrons, these outside electrons, right? This electron is in the third shell. So that's what we're going to talk about in terms of distance, third shell. It's in the third shell. So is this one. So in terms of distance, they're comparable distances from the nucleus, but look at that charge, right? Third shell, but the charge is 11. You know, it's a charge of 11. This thing, the nuclear charge is 17. So 17. So this guy is going to feel a much stronger attraction than this one, because they're approximately the same distance, but there's more positive charge here in the center. And that's true for all of these electrons, right? All of these electrons have that charge of 17 that they feel. So this thing is going to shrink. This thing's going to shrink. This atom is going to be smaller than this atom. It's going to be smaller. And because it's smaller, now the size is smaller, right? And because the size is smaller, now there's more attraction. So there's actually kind of a two-step process here that shows you that the chlorine is going to have a much stronger pull for electrons than the sodium will. And that's because the effective nuclear charge, the charge itself is higher, but also because they're both in the third shell, the effective charge is also higher, right? So that's one thing to talk about. And then the other thing about effective nuclear charge is, let's talk about what happens when we move down a row, down a period. No, down a row. Down a row is correct. Let's talk about the next one down, which is bromine. If we take bromine, right? It's got the same Lewis structure, but the center is now going to have 35 protons, because that is bromine's atomic number. But now it has 4 shells. 2, 3, 4. 1, 2, 3, 4 shells. And I'm not going to bother filling in these, but the outside shell for bromine has, well, we would put 8 valence. We would put 7 valence there because it's a valence of 7. But now there's 4 shells. Right? This one here, this here, any one of these electrons, doesn't matter. That one is now in the 4th shell. And the nuclear charge is 35. right? 35 positives, because that's bromine. Right? This is bromine. And the question is, which one of these two has the stronger pull for electrons? Which one of these two has the stronger pull for electrons? Well, this is where we now have to compare the amount of charge to the distance, right? Bromine has pretty much twice the nuclear charge as chlorine. But in terms of effectiveness of that nuclear charge, right, these are further away. They're in the fourth shell. It's a longer distance. So what's more important, distance or amount of charge? And if you remember what I was talking about with the balloon, the amount of charge is linear. Twice the charge means twice the attraction. But the distance is quadratic, right? So twice the distance is 4 times less attraction. And as it happens in chemicals, in elements, the distance of the next shell is markedly further than the previous shell. And the distance is more important than the amount of charge. So because distance is more important, the fact that this is in the fourth shell means that the effective nuclear charge is actually lower for bromine. So these electrons are held less tightly than these electrons. And the same thing happens, from sodium down to potassium, because that's a fourth shell issue as well. It's a fourth shell with 19 protons instead of 11 protons, and it will also have a lower pull. So distance is more important than charge is what we're trying to get at here. Distance is more important than charge. That's an overview of electrical force concepts. That's what we were doing for electrical force. That's an effective nuclear charge. So the curriculum wants you to be able to explain the concept of effective nuclear charge and then use it to explain why one thing might have more attraction than another. So in this scenario here, in terms of effective nuclear charge, this is number 1 for effective nuclear charge. That's number 1. For effective nuclear charge. Sodium versus bromine. Bromine, I believe, is number 2, and sodium is number 3. Because even though distance is more important, this is just a very low amount of protons compared to 35 is a lot of protons, kind of thing. Also, this would be relatively compact as well. So yeah, in terms of effective nuclear charge, this is number 1. In terms of actual nuclear charge, this is number 1. So the difference between effective nuclear charge and actual nuclear charge is a big part of these trends, and that's why we cover it in detail. Okay, so I'm going to pause and we're going to go to our trends that we can now explain using effective nuclear charge. Okay, so now we're going to talk about the trends that the curriculum wants us to know. Now that we know the concept of effective nuclear charge, we have this rule up here that says that distance, which is the number of shells, is more important than charge, which is the number of protons. If you have to make that call. First off, what's an ion? Because our first topic is ionization energy. An ion is a charged atom. So it's an atom that has gained or lost electrons. Protons can't leave the nucleus. If the proton number changes, you've got a different element. So we don't talk about changes in proton number. We only talk about changes in electron number. So ions are created by gaining or losing electrons. An atom that loses electrons becomes a positive ion. An atom that gains electrons becomes a negative ion. We'll talk more about that when we talk about naming, which is the next video. So these trends, there's electronegativity and there's first ionization energy. Now electronegativity, this guy here, probably the most important trend, but it's very related to first ionization energy, so we're going to talk about both. Electronegativity is a measure of how much the atom wants an electron on a scale of 0 to 4. Basically, it's pull for an electron, right? These things don't want. They're just dumb. They have just protons and electrons and neutrons. They attract electrons to themselves. And so electronegativity is trying to measure what the relative attractive force for electrons is. Now, first ionization energy is very similar. It's the amount of energy that's required to remove an electron from the atom. As you can imagine, they're going to have very similar trends because the pull for an electron, the pull for an outside electron, is very similar to the amount of energy it would take to remove an electron. So I've got some images here. This is ionization energy as a table. And this is, let me find electronegativity here. Here's an electronegativity table. I'm going to put my stuff down in the corner here. So here's an electronegativity table. You can see that these guys don't want electrons very much. These guys do want electrons a lot. And if we go to the ionization energy table, which is this one, you see that the ionization energy for these guys is very high, and the ionization for these guys is very low. So the trends are very similar. Take that away. Both of these trends will increase in a direction from bottom left to top right. Bottom left to top right. So just pulling this up again, you see that the bottom left has the lowest ionization energy, and the top right has the highest ionization energy, right? It increases bottom left to top right. So it increases going upwards, and it increases going to the right. If we go over to electronegativity here, you see the same trend. It increases going upwards, and it increases going to the right. Increases going upwards, increases going to the right. So this bottom left to top right thing. There's a few exceptions, like there's some weird stuff happening in the transition metals. We already talked about that. Transition metals are strange. So, it doesn't necessarily increase going to the right all the time. So, a good example here, from chromium to manganese, it actually drops. Then goes back up for iron, and up, 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 up. That's the general trend. I'll take that away. Right, increases in a direction like that. But the curriculum doesn't just want you to know the trend. It wants you to be able to explain why does it increase. Why does it increase moving from bottom left to top right? And guess what? That's down to effective nuclear charge. So move across a period. Remember, periods are the rows of the table. Atoms get closer to a full shell. They get a better pull, a better effective nuclear charge. Why do they get a better effective nuclear charge? Well, if we go back to here, sodium versus chlorine, and they're in the same row, right? They're in the same row. Sodium's here, chlorine's here. Sodium has just a charge of 11 with 3 shells. Chlorine has a charge of 17 with 3 shells. Same number of shells, but more positive, and so this will have a stronger pull. And bromine, if you move up a thing, you've got fewer shells, so the distance becomes smaller. So this nuclear charge becomes more effective, because the distance is smaller, and so chlorine has a stronger pull than bromine. So back to this guy, right? Y part 2, right? This is the same thing. This is what I'm trying to talk about. The larger number of shells pushes the electrons further away, so you get a weaker hold, and it's less likely to gain new electrons. So that's where this trend comes from, right? Electronegativity in particular is a very important trend. If you look down the table, down around rubidium and cesium in the bottom left, a very, very low electronegativity, because these are big atoms with low nuclear charges compared to something like astatine over on the other side. 55 protons for cesium, 85 protons for astatine on the bottom right. But both of them have 6 shells. So very far out, and a relatively low charge in the nucleus, so very low effective nuclear charge. Up in the other corner, right, if we go up to the other corner, fluorine has 9 protons but only 2 shells. So those electrons are very close in. The effective nuclear charge is very high, so fluorine has a very strong pull for electrons. And that means that it has both a large ionization energy and a large electronegativity. It's the most electronegative substance. Now there is one exception, one interesting difference here that I want to talk about, and that is noble gases. Right? Fluorine has a high ionization energy and a high electronegativity, but if we go over to the ionization energy, the noble gases have even higher ionization energies, but they don't have really a rating for electronegativity because they're stable. It's very hard to add electrons to them. It's also very hard to pull electrons away from them. So, yeah, that's ionization energy. Okay, so that's that one. The last piece here is atomic size. Now you might imagine atomic size has a lot to do with the same thing, effective nuclear charge, because the protons pull on the electrons, bring them closer in. So let's take that away. I'm going to pause and talk about nuclear size for a second. Okay, so the last trend is nuclear size. Same, keep in mind up there, distance is more important than charge. But atomic radius, which is measured in picometers, if I move over here, it's measured in picometers, which pico is very, 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 very small. It's the distance from the nucleus to the furthest electron shell, to the outside electron shell. It's measured in picometers. Picometers are tiny. It increases in a direction, in a downwards direction. I guess that's wrong because of my mirrored thing. It increases opposite to electronegativity and opposite to ionization energy. The reason for that should be pretty obvious, but we can explain why, right? If you move down a group, you get more shells. So naturally you're going to get bigger. Right? If we go over here, chlorine versus bromine, bromine just has more shells, so it's a bigger atom. You can't get away from that. Distance is more important than charge. But moving across a period, right? Moving across a period from sodium to chlorine, the chlorine has more protons in the center with the same number of shells, so they'll pull in more. So chlorine's going to be a smaller atom than sodium. If we take a look at it in terms of a size thing, here's a graph of it. You can see a clear periodic trend in the size. And here's an actual diagram of the size of these things. You can clearly tell that sodium is much bigger than chlorine, right? Much, much, much bigger. 190 versus 79 picometers. And you see that trend increasing going down a group and decreasing going across a row. And you should be able to explain that using effective nuclear charge and number of electron shells. That's what we're very, very interested in here. Okay, one last thing just for fun. Ionization energy is using electricity to give these electrons a kick, and because different elements have different electron shells and different jumps that the electrons can do, you actually get different colors. So you get helium versus neon versus argon versus krypton versus xenon. They make different colors. That's how fireworks work. Instead of electricity, you use heat to give the electrons a kick, but it's the same idea. You get different really cool colors out of your different elements. And that's where a lot of these studies come from, is basically just zapping them with electricity to find out how strongly they hold on to that first electron, how much energy it takes to rip that first electron off. That's where you get cool graphs like this one. Here's the ionization energy across the periodic table, and you see this very obvious periodic trend to it. So that's periodic trends as a video. Hope you enjoyed it. Hope you enjoyed my stupid balloon thing. Remember, what was important was why are trends important to study, this concept of effective nuclear charge, and what that means for atomic size, ionization energy, and electronegativity. Yeah, that's it. That's 40 minutes. So I will see you guys in class.